Hi everyone, in this video we will be solving a problem with two concepts. One is the torsional vibrations of a two rotor system and the torsionally equivalent shaft. So here you can see a shaft which is carrying two rotors A and B at its ends, where this shaft is of stepped one. That means it is having different diameters and different length. That means it is having a length of 300 mm where diameter is 100 mm and next 160 150. Similarly, four steps are there. So you first step you will be converting this stepped shaft into a torsionally equivalent shaft where it is having uniform diameter throughout its entire length, and that equivalent diameter is known as DE and the equivalent length is LE. And since it is a two rotor system, here you will be finding the or locating the node which is coming within this point which is unaffected by this torsional vibration, and then you will be finding the natural frequency of this torsional vibrations. Here the mass of rotor A and its radius of gyration is given, and similarly the details of the rotor B is also given. So we have to solve the problem for finding the natural frequency and we have to locate the node point correctly. So first step is to find the equivalent shaft, that is torsionally equivalent shaft. So here we are having the equation from the previous discussion, that is if the length of the equivalent shaft is LE and its diameter is DE. Here since nothing is mentioned, usually we will be taking some of the existing diameters of the stepped shaft as the diameter of the equivalent. So here four diameters are there, D1, D2, D3 and D4, which values are given. So finally we will be converting this shaft or this stepped shaft into a single diameter that is corresponding to the diameter D1. So this DE we are taking it as corresponding to the value of D1. So you can write the equation L equivalent divided by D equivalent raised to 4. We have derived this one or we have obtained this relation in the previous lectures. So LE divided by D raised to 4 will be equal to L1 by D1 raised to 4 plus L2 by D1 raised to 4 and up to the fourth section, that is L4 divided by D4 raised to 4. So here we have to find the equivalent length of the shaft if the shaft is made up of a single section having diameter corresponding to D1, that is DE equal to D1, which is equal to 100 mm. So you can multiply all terms by D1 raised to 4, then left hand side will be becoming LE and the right hand side will be becoming first term L1 into D1 raised to 4 by D1 raised to 4, which is L1. Next it will be becoming L2 into D1 by D2 the whole raised to 4, L3 into D1 by D3 the whole raised to 4 and L4 into D1 by D4 the whole raised to 4. So if you are substituting the values, the equivalent length you will be getting. So this L1 will be coming as such if the L1 is 300 mm, and then here also it will be contributing a length of 300 mm. And L2 value is 160 mm, D1, D2 values you are having. So if you are calculating, this part will be contributing up to 31.6 mm in the equivalent shaft. And finally this will be having a contribution of 60.2 mm, and this last part is coming around 609.7 mm. So sum of all this value will be giving you the equivalent length of the shaft corresponding to the single diameter, and that value is around 1001.5 mm, or in another words, if you are converting this into meters, then this LE is equal to 1.0015 meter. That means, so this diameter D1 100 mm is coming as whole, that means the entire 300 mm is coming here, and next length is 31, that means here length will be 31.6, but here diameter is 100 mm, and that is corresponding to this 150 mm part which is of length 160 mm, and next 120 mm diameter part having 125 mm length is coming to a length of only 60.2 here, that will be coming somewhat corresponding to here. And finally this 90 mm diameter of 400 mm length will be coming to this maximum 609.7 mm for that 100 mm diameter. Anyway, finally we are having this equivalent shaft of diameter 100 mm and equivalent length of 1.0015 meter. So this individual contributions towards this equivalent length is important because we will be referring to these values later to solve some part of the question. So now you are having this torsionally equivalent shaft. Using this one you will be evaluating the natural frequency and also locating the node. So now we are having a single diameter shaft whose diameter DE, which is equal to D1, is equal to 100 mm, and you're having the equivalent length which is of 1.0015 meter or 1,001.5 mm. So you are knowing the concept of knot. So there will be a point where it is unaffected by the torsional vibration, and on one side it will be twisting in one direction and the other side will be in the opposite direction. And you can locate the knot position with respect to the rotor. So if the left rotor is A and its mass moment of inertia is IA and the other one is B and IB, so you can calculate the mass moment of inertia IA is equal to, mass is given, ma into the radius of gyration square, ma into ka square, whose values are given, which is 300 and 0.75. So it is 300 into 0.75 square. And similarly, the mass moment of inertia rotor B will be equal to mb into kb square, which is 500 kg into 0.9 square. So this IA and IB value you are having. So we have studied in the previous lectures for this two rotor system. You will be splitting this two rotor system into two single rotor system based on this node point. Then its natural frequency of those two parts will be same, and from that concept you have derived a relation connecting this IA and length LA. That means the location of the node. That is, the product of LA and IA will be equal to the product of LB and IB. So here unknown is actually LA and LB. That is the position of the node within this equivalent shaft. So you are having this values of IA here, IB here, and LA is here, but you can represent this LA plus LB as equivalent length, that is 1.0015. So here you can keep this variable LA as such, and you can replace this LB by 1.0015 minus LA. So finally there will be only one variable in terms of LA, and you can solve for this one, and then you will be getting the LA as 0.707 meter or 707 mm. So this is the position of the node within this torsionally equivalent shaft only. In the next step, we will be calculating the position of this node in the actual stepped shaft. That procedure I will be showing now. Before that, we have to find the frequency of the natural vibrations of this system, frequency of this torsional vibration of the system. For that, you can calculate omega n is equal to square root of q equivalent, q of this first part A divided by IA. So this is corresponding to the one side of the knot with respect to the rotor, and this you can evaluate by G into J divided by LA. So G value is given in the question. So G is around 84 gigapascal. If it is not given, you can take this value as 84 into 10 raised to 9 Newton per meter square, and J is equal to pi d raised to 4 by 32, where this diameter is actually the diameter of equivalent shaft. So this will be becoming pi by 32 into 0.1 raised to 4. That value you can evaluate, and LA value now you are having, which is 0.707 meter. All values we are substituting in the SI unit, and finally IA also we have evaluated here, that is MA into K square. And from this you will be getting the value of omega n as 82.93 radians per second. So this value you can evaluate with respect to the rotor B also, where it is becoming QB divided by IB. That is, QB you can evaluate by G into J divided by LB, and IB you are already having. Anyway, that value will be coming as same as this 82.93 radians per second. So we have evaluated the location of the node within the torsionally equivalent shaft, and also we have evaluated the natural frequency, but we have to locate the position of the node in the actual stepped shaft, that we will be seeing. So in the torsionally equivalent shaft, the location of node is at a length LA, that is from the rotor, left rotor A, at a length of 0.707 meter or 707 mm is coming up to this position. So using the previous values, we will be evaluating, or we will be finding the position of the node in the actual stepped system. So here in the torsionally equivalent shaft, this node is coming somewhat here. That means this length is it is coming here. This is the position of node, and you are not knowing where the node is coming in the actual one. Anyway, this length is 707 mm. So in the first stage we have evaluated the equivalent or the contribution of each parts of the stepped shaft into the equivalent length. That means this entire 300 mm is contributing to the equivalent length of this torsional equivalent shaft. 160 mm of 150 mm diameter is becoming only 31.6 of 100 mm diameter. Similarly, this 120 mm diameter part of 125 mm long is becoming, or it is contributing only up to 60.92. So if you are adding all these values, that means if you are adding all these three values, then this will be coming around 391.8 mm only. But the node is at a position of 707 mm from the left end. That means still we have covered this three portions that is corresponding to this three stepped parts. So still there is some more length that is remaining, that is the 707 minus 391.8, that is 707 minus 391.8, which is of 309.2 mm. So 309.2 mm is coming from this 609.7 mm, that is, it is coming from this last part. That means in the actual system the node will be coming somewhere here, and this distance you have to evaluate. Suppose this distance is x, and you have to evaluate the distance x from this one. So the length in this one is x, and in the torsionally equivalent one is 309.2 mm. So you can relate the similar equation L equivalent for this part only as x into d1 divided by d4 raised to 4. So if you are solving this one, then you will be getting the value of x. So this LE is, you can substitute in mm. So this LE is 309.2 in equivalent, and this x you have to evaluate, and the d1, that is the equivalent diameter, which is 100, and d4 is 90, the whole raised to 4. So if you are solving this one, then you will be getting the value of x. So x will be coming as 202.8 mm. That means in the actual shaft, the node will be coming at a length of 202.8 mm from this point. Or you can evaluate in the actual shaft this total distance by using, or by finding the sum of all these four values, that is 300 plus 160 plus 125 plus this 202.8. Anyway, the position of node will be coming here in this stepped shaft system, but this is evaluated by making use of the torsional equal. This concept is somewhat it will be taking some time to understand. Anyway, you can analyze very step by step, then you will be getting all these things clearly. So try to understand these things. So this is the way how you can deal with this two rotor system and this stepped shaft or torsionally equivalent shaft system. So hope you understood this one, and thanks for watching.